So, what to talk about today? I think we should probably talk about the precise definition of a limit, also known as the delta-epsilon proof. Let's do that. Precise definition of, I'm going to want more colors here. Cool. Good thing I have more colors. So, let's look at the following example. We're going to look at the function f of x equal to 2x plus 1. And the idea here is we're going to look at what happens. So here's what we're thinking. We are thinking about the limit as x approaches 3 of 2x plus 1. And if we plugged in 3, we can see the limit's definitely going to be 7. And that's all well and good as far as evaluating the limit. But if you're actually trying to, quote unquote, prove that the limit is equal to what it's equal to, there's more to it than just saying it's 7. So we're going to walk through some of the idea pieces first, and then we'll kind of build up to how to write this quote unquote proof. So we're going to draw or sketch the following two things. One, the piece or portion of this function where the difference between the function and the limit is small. Say, not that small. Let's say it's less than 1. I want to make this exceptionally clear. When you see this notation here, the absolute value of f of x minus something less than something, what you should be thinking is, oh, the function is close to 7. How close? Within 1. So let's draw it. So, yeah, I never have enough room. Fine. So I was drawing 2x plus 1. I'm going to try and draw it kind of nicely here. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sure. There's 7. There's 3. Now let's see. I'm going to plot a few points. So if x is 2, 5. Sorry, my graph's doesn't look that good. And then when x is 3, I get 7. And when x is 4, I get 9. Now I'm actually graphing a little bit too much here. So I'm going to kind of draw it dashed for a second. So I'm going to have like this. So here's the line. Y equals 2x plus 1. And then if I want the function to be within 1 of 7, well, if I actually solve this inequality, that means f of x minus 7 is less than 1, bigger than negative 1. Or in other words, f of x, my function, is between, if I add 7, 8 and 6. So I'm looking at this part of the graph where the function is between 6 and 8. And I'm going to draw it again, even though it feels a little bit silly. And I'll try to actually kind of think about what x values we have here. Okay, we're going to draw another thing, although it's really going to be the same. But I should actually write a few more words here. I want to say that the absolute value of f of x minus 7 less than 1 is the portion of the graph containing all y values within 1 of 7. And not exactly surprising, but good to see. Okay, now we're going to do a similar thing, which is going to feel the same, but it's slightly different. So here we're going to sketch something else. So now we're going to sketch part 2, the piece of the same function, where instead of caring about where the function values are, we're going to ask where the x values are. So we're going to say we want the x values to be within 1/2 of 3. And again, I'll say the same thing I said before, just like up here. I can't quite see that. We're gonna have a little more vertical room here. Just like up here, I was encouraging you to think of this when you read this, say, oh yeah, that means the function is close to 7. How close? Within that much. Same idea here. Now we're going to graph the piece where x is close to 3. How close? Within 1/2 of 3. So let's do it. Sorry to throw my graphing skills on you like this, but they're not that great. Such is life. They're fine. So same graph, y equals 2x plus 1. So I know I still have the point 1, 3, and 0, 1, and 2, 5. Trying to make this look somewhat decent. 3, 7, 4, 9. So here's the graph. But now I want to limit the x values to being within 1/2 of 3. So 1/2 to the right, 1/2 to the left. We could also solve the inequality. X minus 3 is less than 1/2, bigger than negative 1/2. We add 3 to both sides, all sides. X is less than 3.5, or 7/2 if you prefer. X is bigger than 3 minus 1/2, which is 2.5, or 5/2 if you prefer. So we're between here and here. And if we kind of go up this way, what we're going to see is that we get the same piece of the graph that we had before. I know I've not drawn it perfectly, but it looks pretty similar. So, excuse me. What I want to point out is that x minus 3 less than 1/2 is the portion of the graph. I'm just writing the words I've said. Portion of is the portion of the graph containing x values. Yes, I was just about to say, I feel like I'm kind of low here. Containing x values within 1/2 of 3. And these are the same. This is important because what we're going to do is we're going to say, well, I want to make the function values as close to the limit as possible by finding how close x needs to be so that we achieve that result. So here's another way of wording what we've just done. And I will point out, there's a lot of words involved in this process, right? It's not just writing mathematical symbols and numbers. You also have to write some actual words sometimes for math. I know it's kind of terrible, but we're stuck with it. So here's what I want you to see. Paper stays as I like to do. So observe that the absolute value of f of x minus 7 being less than 1 and the absolute value of x minus 3 being less than 1/2 describe the exact same portion of the graph. So let's get a little bit more refined. Let's say instead, now we really want f of x equal to 2x plus 1 to be closer to the value of 7. In fact, what we really want is we want the absolute value of f of x minus 7 to be less than 1/10. And the question we want to answer, preferably without graphing it, but we're going to graph it anyway, is how close does x need to be to 3 so that the function is this close to 7? Great, let's graph it. But try not to do all the, well, we're going to graph it kind of, but we're really going to do the algebra. Here's my graph. The 3 is about right there. 7 is about right there. And what we would like to happen is we would like our function f of x minus 7, the difference between our function and 7, to be pretty small. Let's actually rewrite it using the function. That's going to be the same as saying 2x plus 1 minus 7 in absolute value is less than 1/10. Now, there's a couple ways to go here. What I want you to see, first of all, is what this really means is that I have that 2x plus 1 is either a 10th above 7 or a 10th below 7. I should say as much as a 10th above or as much as a 10th below. So this is going to look not quite to scale. So we're up here as high as 7 plus a 10th, or as low as 7 minus a 10th. Yes, we could say that's 7.1 and 6.9. But what we're trying to figure out here is, what are the corresponding kind of limits on x? Well, it's usually, yeah. Sorry, there's a couple different schools of thought here. I would say if your function is linear, it's usually pretty easy. If it's non-linear, it's a little hard. But for the linear ones, you can actually make your life super easy and try to just manipulate this so that the absolute value looks like the thing you're trying to get to, the absolute value of x minus 3. So I can simplify this. It's the absolute value of 2x minus 6. I can factor out a 2. So the absolute value of 2 times x minus 3 is less than 1/10. I can bring the 2 outside the absolute value, or really technically what we're actually doing is saying if you have the absolute value of a product, it's equal to the absolute value of 2 times the absolute value of x minus 3, which seems reasonable, right? If you have the absolute value of two things multiplied together, well, as long as both of them are already positive, the result's still going to be positive when you multiply them together. So you can just take the absolute value of each part. But we didn't really need to write the absolute value of 2 because it's already positive. Note, if this was a negative 2, right, if my line was negative 2x plus 1, then when we factored out that negative 2 and then took the absolute value of it, it would come out as positive. Because the number that's over here really has to be positive. So if we're going to divide by 2, that thing needs to be positive. Dividing by negative would be harmful here. Dividing both sides by 2, we get the absolute value of x minus 3 is less than 1/20. So what that tells us is that, great, as long as x is within 1/20th of 3, so we're either 1/20th to the right or 1/20th to the left, then our function will be within 1/10 of 7. Or using the language that we typically use here, if we let delta equal 1/20th, then the absolute value of x minus 3 less than that number will give us that the absolute value of f of x minus the limit value is less than the desired value, which we typically call epsilon. Lowercase epsilon, lowercase. I had a water bottle somewhere, I think. Yeah, thanks. Like it just disappeared. Yes. Sure. In fact, the next example we do will have a negative. Yes, but yeah. So let's look at some examples. Yeah. Let me just sure. Well, actually, so we're gonna write the proof here for this one, and then we'll do another one where the slope is negative. So part of this depends on the style your instructor prefers. People have different kind of words they like to use when they write these kind of proofs. I'll show you the way I think is concise, and then we can go from there. So we want to prove that the limit as x approaches 3 of 2x plus 1 is equal to 7. So my personal preference is to do the following. And this is kind of the thing people say sometimes when you're proving something, you do 3 things. You tell them what you're going to tell them. And then you tell them, what you told them. So this seems like overkill, but it's helpful. So first, we're just going to say what we're going to do. All right, so here's what we want to do. And I have to remember this. It's been a minute, so I need to remember this. So we want to show that, well, we want to show that this limit's equal to that. What that really means is that we want to show that if x is close enough to 3, then the function is as close to 7 as we want. So we want to show that for any epsilon that is greater than 0, you're usually imagining that epsilon is some pretty small number, though it can really be any positive number, but we think of it as being small, that there exists, or we can find, but I'd say there exists, a delta that is also positive, such that, people like to use an implications error here. I like to use an if-then, but it's the same thing, such that if the absolute value of x minus 3 is less than delta, oh, and I should say greater than 0. Your instructor, I think, one of your instructors like to use the implies arrow here. It's totally fine. I like to use a comma and say, then the absolute value of f of x minus 7 is less than epsilon. That's what we are trying to do. We are trying to show that if x is close enough to 3, then f of x is as close to 7 as we want to get, which proves the limit is what it is, because that says, okay, great. The closer and closer x gets to 3, the closer and closer f of x gets to 7. It feels, I will say, when I learned this, taking 21A too many years ago at this school, I thought it was really dumb. I was like, why are we doing this? It seems like a waste of time. It's just like, And a lie for many of you, it is. If you're not a math major, you probably don't really care about this, to be perfectly honest. That doesn't mean it's not important. It's kind of the basis for how all of calculus works, is this idea that we can prove a limit is actually what it's equal to. But as far as moving forward in your mathematical careers, you might see this again or something similar-ish in 21B. And if you're a math major, you'll definitely see this when you take the 127 series. But if you're not a math major, this idea, once you've done it in 21A, you get to leave it behind and you're like, great, it's in a box over here. We can never touch it again. But for now, it's what we're doing. So this is what we want to do. So what we usually then do is we start with the thing we're trying to get to. So we start with this and we work backwards to this. So I say, great, we want the absolute value. I'm actually going to use the function of 2x plus 1 minus 7. Come on, James. Sorry about that. That's terrible. To be less than epsilon. Now we're going to manipulate this until it looks like that, which is, again, not too terrible. 1 minus 7 is negative 6. So we have the absolute value of 2x minus 6 less than epsilon. We can factor out the 2. So we get 2 times the absolute value of x minus 3 less than epsilon. And finally, we get the absolute value of x minus 3 less than epsilon over 2. And that, epsilon over 2, that's our choice for delta in this problem. This is our delta. And we can see that from the actual numerical examples we already did. We saw that for the function to be within 1 of 7, x had to be within 1/2 of 3. And for the function to be within 1/10 of 7, x had to be within 1/2 of 1/10, or 1/20th of 3. So however close we want the function to be to 7, in this problem, x has to be as close by, closer by a factor of 2, right? The difference between x and the number 3 has to be half as big as this difference here. Epsilon divided by 2 instead of just epsilon. Which is right where we got to right here, right? We said, oh yeah, we just did some algebra, we simplified that, we factored out the 2, we divided by 2, and we're getting that the absolute value of x minus 3 is less than epsilon divided by 2. So then here's the words I like to write. I probably should have written we want, but okay, fine. So here's what we do. We pick or choose delta equal to epsilon over 2. And then the amount of writing you do here is a matter of personal choice. I like to point out, though, we kind of already did all the work we needed to do up here. So we say, great. Then if the absolute value of x minus 3 is less than our choice for delta, we can conclude, and you can write this out if you want to, right? You could be like, okay, then we get this, then we get this, then we get this. We can conclude that absolute value of 2x plus 1 minus 7 is less than epsilon, which is exactly what we wanted to say. We wanted to say, great, if x is really close to 3, then f of x is as close to 7 as we want it to be. And then I usually like to write the words, this proves or shows that the limit as x approaches 3 of 2x plus 1 is equal to 7. And then people like to write like a little, they make a little square and then fill it in, which is a shorthand notation for we proved the thing we wanted. We're done. I probably write more words than are necessary. That's okay. But you can probably write less and be fine. I will point out this function, and again, we shouldn't be surprised here, right? We know that the function 2x plus 1 literally goes to the point 3 comma 7. But what we're saying here is that we can pick epsilon to be any number we want. We can pick epsilon to be 1/1 billionth. And if we pick delta to be 1/2 billionth, right? 1/1 billionth divided by 2, then x will be close enough to 3 so that our function is as close to 7 as we just said we wanted it to be. It feels kind of like we're talking in circles, like it's like we want the thing, we do the thing, we get the thing, right? But we actually are accomplishing something. We are proving that this limit is what it is. So let's do another example. We'll kind of talk about the work we need to show. Try not to get my papers out of order here. Let's look at this next example here. So let's look at the following. We want to prove the limit as x approaches 2 of negative 5x plus, I don't know, 13 is equal to negative 10 plus 13 is 3. So that's our job. And honestly, before I start writing out the proof, I like to do the algebra. So here is my side work. The work I'm not really submitting, I'm just kind of doing. So I know here's what I want. I want the absolute value of f of x minus my limit to be less than epsilon. Or in other words, the absolute value of negative 5x plus 13 minus 3 to be less than my epsilon. And we're trying to get to something like the absolute value of x minus whatever x is approaching, which is 2 in this case, to be less than some delta. And that delta needs to be in terms of epsilon. So the idea here is we're going to work with this until we get to something that looks like that. Okay, so let's see here. Simplify, I have the absolute value of negative 5x, 13 minus 3 is plus 10, less than epsilon. So now here's how this one's slightly different. I'm going to factor out the negative 5, but still inside the absolute value. So it's going to be the absolute value of negative 5 times x minus 2. And now the absolute value of negative 5 times x minus 2, well, whatever it is, it should be positive. Well, that's going to be the same as the absolute value of negative 5 times the absolute value of x minus 2. But what's the absolute value of negative 5? Right. But for the other one, I didn't actually need to even write it because I already knew it was going to be positive. But here I'm, okay, a little bit more careful here. So I have 5 times the absolute value of x minus 2 is less than epsilon. Or in other words, the absolute value of x minus 2 is less than epsilon divided by 5. So delta equal to epsilon divided by 5 is going to be our choice for delta. I will say, because it's true, that for linear functions, like f of x equal to some mx plus b, whether your m is positive or negative, your delta always ends up being epsilon divided by the absolute value of the slope. you still should show the work. And again, there's other problems that are non-linear that definitely you have to do other stuff for. But for linear ones, you can make that jump. So let's write the proof. I'll try to write it using less words now. So here's our proof. We want to show for any epsilon greater than 0, there exists or there is a delta greater than 0 such that the absolute value of x minus 2 less than delta gives us that the absolute value of f of x, which is negative 5x plus 13 minus 3, is less than epsilon. This says we want to show for any epsilon greater than 0, there is a delta greater than 0. Fair question. Such that, which I have to abbreviate as ST. The absolute value of x minus 2 is less than delta, gives us that the absolute value of negative 5x plus 13 minus 3 is less than epsilon. Great, we've already done all the work we need, so here's what we're going to do. We're just going to say pick delta equal to epsilon over 5. Then we can, I'm going to show more work. I know I said it's going to be shorter. It's not true. Then the absolute value of x minus 2 less than epsilon over 5 implies that 5 times the absolute value of x minus 2 is less than epsilon, implies that the absolute value of negative 5 times x minus 2 is less than epsilon. I'm just working backwards. Implies that the absolute value of negative 5x plus 10 is less than epsilon. Implies that the absolute value of negative 5x plus 13 minus 3 is less than epsilon, which is our f of x minus our limit. We did it. We showed the thing we wanted to show. We showed that if x is really close to 2, then f of x is really close to the limit. This proves the limit as x approaches 2 of negative 5x plus 13 is equal to 3. I am not good at writing these using less words. I apologize for that because this is what you've got. I'll try to do a few where it's a little bit less wordy, but yeah. So for these ones that are linear, they're not too bad. Our job is to figure out what delta needs to be and then say, great. We want to find for any epsilon greater than 0, a delta greater than 0 such that if x minus 2 is less than, or x minus whatever x is approaching is less than delta, then the absolute value of our function minus its limit is less than epsilon. All right, let's do yes.
So for the proof, it says where, and is that, what does that say after that? We want to show for any.
So let's do another one where I write it a little bit more nicely. But so this says we want to show, and I feel like the words I picked are not the best. So I'm going to try and streamline. I will actually try to streamline my words for one more of these. We want to show for any epsilon greater than 0, there is a delta greater than 0 such that what I really wanted to write here actually was if the absolute value of x minus 2 is less than delta, then the absolute value of negative 5x plus 13 is minus 3 is less than epsilon. Those are the words I really should have written, but I forgot a word and then got off. And then we picked delta to be the thing we found it to be over here. And then we kind of work back through. Then x minus 2 and absolute value being less than our choice gives us, we kind of work backwards to this until we get to the f of x minus the limit less than epsilon. Well, let me show you the other one. I'll try to go a little bit slower and say more. Well, say more and write less. So let's look at the following example. We're really going to do it this time. I'm not just kidding. The limit as x approaches negative 4 I never like the choice of 3 here, so let's go 7x plus 5 is equal to negative 23. We're still going to show the work, but I want you all to tell me when we find our delta should be epsilon divided by what? I heard some of you whispering or sound. People sound like snakes over here because it's epsilon divided by 7. That's what we're going to get eventually. Again, this only works for linear functions. I will point out if that was a negative 7x, it would still be epsilon divided by positive 7. Okay, but we're still gonna show the work. So here's our side work. We're gonna start with the absolute value of our function minus the limit less than epsilon, which becomes the absolute value of 7x plus 5 minus negative 23 less than epsilon. Simplifying, we have the absolute value of 7x plus 28 less than epsilon. Not surprisingly, we can factor out a 7. So left with an absolute value of x plus 4. And I wouldn't probably normally write it this way, but I'm going to this time. I'm going to write this as epsilon over 7 over here. Instead of x plus 4, x minus minus 4. Just to be super explicit about what we've got going on here. Okay. So I'm going to write this proof in the style of Grant because it is much more concise than the ones I've been writing. So here's our proof. It feels like so little words to write. So here's what we've got. For any epsilon greater than 0, if delta is equal to epsilon over 7, then I'm going to make one modification here. The absolute value of x minus minus 4 less than 7. Sorry, less than what? Less than epsilon. Sorry, that's a terrible. I hate that. Oh. And it's not even right. It's supposed to be less than delta. I got too caught up. Sorry. That is a delta, believe it or not. Let's just delta. That's what I'm supposed to try and do over there. The thing I was trying to say before I got distracted over here is that we should have a greater than 0 here. It is important to note that x is not actually equal to negative 4. Right? That we're getting really, 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 really close to negative 4. We're not actually getting to negative 4 because the limit doesn't care what happens at the value x is approaching. And again, I'm gonna cross this out completely and write it again. It doesn't look like trash. So for any epsilon greater than 0, if delta is equal to epsilon over 7, then we can say that 0 less than the absolute value of x minus negative 4 less than epsilon less than delta. Oh my gosh. Then that implies, by the work we did over here, right? If we just work backwards, that the absolute value of our function minus its limit is less than epsilon. And then we're done. This proves the limit as x approaches negative 4 of 7x plus 5 is equal to negative 23. Very bare bones, right? Much, much, much less verbiage than I was using in my examples. We're still getting the point across, right? We're still saying, great, if x is close enough to negative 4, how close? Delta, which is epsilon over 7, then our function will be close enough to its limit negative 23. And again, it makes sense that it would be 1/7 or whatever the slope is because, right, if x is within some numerical value of what we're approaching and it's getting multiplied by 7, that distance between those two things is getting multiplied by 7 as well. So you're getting, if you're within epsilon over 7, then the function's within epsilon over 7 times 7. Yeah. Correct. Neither is delta. Right. So a lot of times, especially in web work problems, it's kind of hard to ask you to write a proof here. So like, for example, if they then said for this problem, if they gave us like, for example, epsilon, geez, epsilon equal to, I don't know, 0.014, and they asked you to find the delta so that the function was that close to the limit value. Well, this work we've done tells us that delta must be epsilon divided by 7, which is 0.014 divided by 7, which is 0.002. And obviously I picked a number that's easy to divide by 7. But if it wasn't easy to write, you could just leave it like that if it doesn't actually divide nicely. So yeah, so if you're asked to find a delta given a specific epsilon, you can kind of just, well, again, if it's a nice linear one like this, it works out really nicely. Your deltas can be epsilon, the given epsilon divided by whatever the numerical value, or sorry, the slope value is. Yes.
In the step thereafter, you factor out the 7.
Yes.
Why did you rewrite the x plus 4 as x minus times x?
Because the usual kind of way of thinking about this is that we are proving that the limit as x approaches c of f of x is equal to L by showing that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. So I was trying to make it so it looked like I had really x minus the value that x was approaching.
Oh,
You don't really need to write it that way, but I was just trying to be super duper explicit about like what's happening here. Oh yeah. The reason, and again, the reason why I had this way is because this really shows that the difference between these two things, x and -4, is getting smaller and smaller and smaller. Or in other words, x is getting closer and closer and closer to -4. And again, let me actually just say that really again. What this really means here, this means that x is really close to c. How close? Delta close. Within delta on either side of c. And this has a similar meaning. This means that f of x is close to L. Because if the difference of two things is small, it means those two things are close to each other. So, to get more excited, let's look at some other examples here. Yeah, classic example, sure. And I think from what I saw, Chan has talked about this, right? But no, I don't think No has yet. From what I saw, it looks like he's doing it kind of this newer way. So when I learned this way back when, it was presented in a slightly different way, but I think he's doing it what I think of now as the regular way of doing it, so we'll do it that way. And yeah, let's just, I know it's, so let's say we want to do the following. We want to prove the limit as x approaches 3 of x squared is equal to 9. And unlike our previous examples, here, the deltas on either side of 3 aren't going to be the same for a particular choice of epsilon. Let me show you what I mean by this graphically. So here's my good old parabola. Something like that. Again, it's not quite to scale. That's fine. So let's pretend like there's 3. Yes, I know that's not really 9, but that's okay. It looks like it. So if we're within epsilon on either side of 9, so if we've gone up to like here, so here's 9 plus epsilon. Down here, the same distance away from 9, here's 9 minus epsilon. If we look over to the function, and I think I've drawn it well enough, maybe, we'll see here. So it might not be super easy to tell based on how I've drawn this. Let me zoom in a little bit here. But since we have a non-linear graph here, the same change in y doesn't correspond to an equal amount of change in x. In fact, since the graph is steeper over here, we're going to get less change in x for the same amount of y, and the graph is less steep here, we're going to get more change in x. So we typically call this like delta 1 and delta 2, and our deltas are not the same. So I'll point out that for a fixed value of epsilon here, we get different deltas on either side of x equal to 3. Let's say c equal to 3. Let's be smarter about that, James. So when this happens, what we typically do is we will choose the minimum of those two deltas. And here's why. If we choose the larger delta value, then we're going to end up going too far to the right, because, right, if we go this far to the left and say that far to the right, bless you, we will end up not being within the given value of epsilon, within epsilon of 9, right? We'll be too far away. So if you get two different delta values on either side of the c that we're approaching, we always pick the smaller of the two, the minimum of the two. And sometimes people do the work to actually figure out which one is the minimum, or sometimes we just say the minimum of them and then leave it at that. Most of the time, you can tell graphically which one's going to be smaller just based on which part of the graph is steeper and which part's less steep. But we don't always have the graph, so then we test. So here's what we're going to do. Let's zoom back out a little bit here. So same idea. We want both things, like I'm saying. So the things we want to be true. We want x to be close to 3. We want our function to be close to 9. Or in other words, we want both x minus 2 to be, sorry, not 2, 3, apologies. X minus 3 in absolute value to be small, and the absolute value of our function minus its limit to be small as well. And we're going to try to figure out essentially what we need to happen over here so that this works over here. So we're going to work on the right-hand side first. So we have the absolute value of x squared minus 9 less than epsilon. And then we're going to rewrite this as a compound inequality. If an absolute value is smaller than a number, it means the inside stuff is smaller than the positive number or bigger than the negative number. And then we're going to try to isolate x. So we're going to add 9 to every side. So x squared is less than 9 plus epsilon, bigger than 9 minus epsilon. And then we're going to take the square root of both sides. So x is between the square root of 9 plus epsilon and the square root of 9 minus epsilon. Over here, we're going to do the same thing. We're going to isolate x. So this one's a little bit easier. We're going to have the absolute, we're going to have x minus 3. Now, normally I would say delta and negative delta, but since we know our deltas are going to be different, we're going to give them different names. So we say this is going to be between delta 2 and delta 1. Typically delta 1 on the left, typically delta 1 on the right, although it doesn't really particularly matter. And then x is going to be between delta 2 plus 3. I feel like I've made, no, I know what I did. I forgot the minus sign here, sorry. So even though we're calling them different, we want to say this one's negative delta 1 because we want x to be able to be smaller than 3, right? So right, if this was a positive number, that would be problematic. So we're giving ourselves the negative here just so we can see it. So we have negative delta 1. Okay, so here's the idea. We're going to set that equal to that to figure out what delta has to be. I should say delta 2. And we're going to set that equal to that. some people do this a little bit differently. I might actually be in the same boat. Some people would just try to make this look like x minus 3, which I kind of feel like is what I'd rather do, but I kind of didn't. So we'll talk about it both ways. You can do it this way and say great, but then, yeah, no, it seems dumb not to do it that way. I don't love this. I would rather stop here instead, honestly, and say, let's work with this and make this, let's subtract 3 from every side. So I've got x minus 3. I feel like there's a reason I don't want to do this, and I'm just forgetting why I don't want to do this. Oh, yeah. Yeah, I see. So I'm sorry. Sometimes your gut instinct is the right one. Apologies. So we will do the, even though I like it less. Sorry about that. So if we set that equal to that, here's what we get. We get delta 2 plus 3 equal to the square root of 9 plus epsilon. Or in other words, delta 2 equal to the square root of 9 plus epsilon minus 3, which is a positive number, because 9 plus epsilon is bigger than 9, square root of that's bigger than 3. And then similarly, we're going to have negative delta 1 plus 3 equal to the square root of 9 minus epsilon, or 3 minus the square root of 9 minus epsilon equal to delta 1. Also positive, because 3 minus the square root of 9 minus epsilon is a little bit bigger than 0, because the square root of 9 minus epsilon is a little bit less than the square root of 9. So you can either, at this point, just kind of punt and say, we're going to pick delta to be the minimum of those two deltas. Or you can figure out which one's smaller, typically just by testing a value. So we could pick kind of any value of epsilon we want that's not 0. And if we do that, well, I'm going to pick something convenient. Something like maybe 5, which I know is really big when you're thinking about epsilons, but is what's going to work for us so that one of those square roots kind of turns out to be nice. So let's see what I mean here. So if delta 1 is equal to 3 minus the square root of 9 minus epsilon, and we pick epsilon equal to 5, we're going to get delta 1 equal to 3 minus, 3 minus the square root of 9 minus 5, which is 3 minus, wow, can I write a minus sign? Square root 4, which is equal to 3 minus 2, which is 1. On the other hand, if epsilon is equal to 5, our delta 2 is going to be the square root of 9 plus 5 minus 3. And I don't know what the square root of 9 plus 5 is, but I know it's less than 4. Because the square root of 14 is less than the square root of 16. So which one's smaller? Delta 1, which is equal to 1, or delta 2, which is less than 1? Delta 2. So the minimum of delta 1 and delta 2 is delta 2. Okay. We still have to write the, okay, question.
We can pick like any value we want for epsilon.
Correct, but any value that's positive. And I'll point out, I'm just picking a numerical value here to help me see which of the two deltas is smaller. Right, but I could have also, so as an alternative, you could have picked 7. Because then square root of 9 plus 7 is square root of 16. 4 minus 3 is 1. So that delta would be 1. And then this delta up here would be 3 minus the square root of 9 minus 7, which is 3 minus the square root of 2, which is like bigger than 1. Right, it's like 3 minus about 1.4, which is about 1.6, bigger than 1. So you're still going to see that this is the smaller of the two. Or you could do none of this work and just say, great, pick delta equal to the minimum of delta 1 and delta 2. Whatever that might be. And often people are totally fine with that. Obviously, it depends on what your instructor wants you to do. So if they say that you actually need to figure out which of the two deltas is the smaller, then you have to figure out which is the smaller. Okay, so then we're almost done. We just have to write the proof. So the proof of the limit as x approaches 3 of x squared equals 9. Again, try to be abbreviated here. So for any epsilon greater than 0, if delta is equal to, what do you find here? The delta 2, which was, I forgot what it was, square root of 9 plus epsilon minus 3. So if delta is equal to the square root of 9 plus epsilon minus 3, then we can say that the absolute value of x minus 3 being less than delta, and what do I need also? Greater than 0, implies that the absolute value of x squared minus 9 is less than epsilon. Done. Although, yes, sorry. Thus, we have proved, I always like to say we proved, that the limit as x approaches 3 of x squared equals 9. It's kind of a giant pain, but it's doable. Yeah. I want to make sure I'm not forgetting anything silly here. No, that's fine. Sure, yes. So let's look at another example here. You want to prove the limit x approaches 3 of 4 over x plus 1 is equal to 1. Which I think we can all see if we plugged in 3 for x, we would certainly get 4 over 4, which is 1. Okay. So, but there's something I'm forgetting with this. It's fine. So we want the following to be true. We both want the absolute value of x minus 3 less than delta. And we want the absolute value of 4 over x plus 1 minus 1 to be less than epsilon. And our goal is to try to make this look like that. We'll see if I can get there. I'll try my best. So I'm just going to start manipulating this. I have 4 over x plus 1 minus 1 less than epsilon, bigger than negative epsilon. Sure, yeah, there's a couple ways to go here. It gets dicey. Yeah, that's fine. Okay. So I'm going to add 1 to everything. So 1 minus epsilon less than 4 over x plus 1 less than epsilon plus 1. Now what? So here's what we typically do at this juncture. If you have an x in your denominator, we typically take the reciprocal of every side. I'll remind you that when we take the reciprocal with an inequality, it changes the order of the inequality. Right? 2 is less than 3, but 1/2 is bigger than 1/3. So if we take the reciprocal of everything here, we're going to have 1 over 1 minus epsilon is bigger than x plus 1 over 4 is bigger than 1 over 1 plus epsilon. Now I'm going to multiply everything by 4. So I've got 4 over 1 minus epsilon is bigger than x plus 1. It's bigger than 4 over 1 plus epsilon. And then let's see here. I guess, so again, I'm trying to do it this other way where I make the middle part here look like what I'm doing here. So I guess I should really subtract 4 from everything. Yeah, that feels fine. So subtract 4 from everything. I have 4 over 1 minus epsilon minus 4 less than x minus 3. Sorry, bigger than. I said less than, but I wrote bigger than. Bigger than 4 over 1 plus epsilon minus 4. Okay, something I want you to observe here. I'm actually going to rewrite this so that it looks like the normal way of writing it. I'm gonna write it as x minus 3 is less than that part. 4 over 1 minus epsilon minus 4, and bigger than that part. 4 over 1 plus epsilon minus 4. So this part over here, 1 minus epsilon is a little bit smaller than 1. 4 divided by that is a little bit bigger than 4. And that minus 4 is a little bit positive. On the other side, this should end up being a little bit negative. And it is, because 1 plus epsilon is a little bigger than 1. 4 divided by a number bigger than 1 is a little less than 4. A number less than 4 minus 4 is a little bit negative. So I just want to point out, and this is where I think I got caught up earlier, is that this right-hand side is what we're going to say is our delta 1. And this left-hand side isn't our delta 2, it's our negative delta 2. Because what we're doing here is we're saying, great, yeah, we want x minus 3 to be between delta 1 and negative delta 2. Because the deltas themselves are positive, but we need the left-hand one to be negative so that it works out correctly. Okay. Question.
Why is it negative? Why is delta 2 negative?
Well, so if these were the same, it wouldn't make sense to say that x minus 3 was less than delta and bigger than the same delta. And they often are the same, right? And like in the previous problems. So the thing here is that even though we're saying that we can go as far as delta to the right or delta to the left, we end up saying, well, delta to the left means we have to subtract delta. So, right, if we say that, like, for x to be, like, say, 2.9 or whatever, 2.9 minus 3 is negative 0.1. So to be bigger than delta, that delta needs to be having a negative sign in front of it. And that's kind of just the way we make it work. So that's really what's happening there. It's just, it's harder to kind of justify that to yourselves when the deltas are negative. You're like, oh, well, one's bigger than the other one, so it's totally fine for x. No, one's positive and one's negative. The one on the right is the positive one, the one on the left is the negative one, so that we can either end up going to the right of 3 and having x minus 3 be positive, or to the left of 3 and having x minus 3 be negative, but still within the threshold that we're looking to be. So then I guess we should figure out which of those is the minimum. So I have to be a little extra careful here. Because if epsilon's too big, I'm going to get too far away. Like, for example, if epsilon's bigger than 1, I think I'm going to have some serious problems. Because then 1 minus epsilon is going to be negative, and 4 over a negative. This whole thing's going to be negative, which is problematic. So I don't want to move too far away so that I don't... Really, the problem is the vertical asymptote with this function. 4 over x plus 1 has a vertical asymptote at x equal to negative 1. And so if we get too far away from what x is approaching, like we get 4 away from it, then it's going to be problematic. So we should be careful and make sure we pick epsilons that are not too terrible. Do I really want to do it? Not really, but it will. So, anyone have a good suggestion for epsilon that's less than 1? I know what I would pick. What's that? Yeah, if I don't have any good inclination to pick something, and I know it has to be less than 1, 1/2 is my usual choice. So I pick epsilon equal to 1/2. Let's see what happens. So the delta 1 is going to equal 4 over 1 minus 1/2. So 4 over 1/2 minus 4, which is 8 minus 4, which is 4. Okay, great. Delta 2, now I should say negative delta 2 really, is equal to 4 over 1 plus 1/2 minus 4. 4 divided by 3/2 is like 4 multiplied by 2/3. That's going to be 8/3. Minus 4 is minus 12/3, which is negative 4/3. So it looks like my delta 2 is positive 4/3. And of the two of those, 4/3 is definitely smaller than 4. So delta 2 is our smaller one. I will also point out, if you looked at the graph of this, and we didn't. If we did, We'll go back up here for a second. So I'm sorry, I know it's hard to leave all work. So if we look at the graph of f of x equal to 4 over x plus 1, it's kind of a typical reciprocal function, shifted one left and multiplied by a factor of 4. So that function is going to have a vertical asymptote at -1. And then it's going to look kind of like, let's see, 1, 2, 3, 4. It's going to come down like this. Getting shallower and shallower as we move to the right. So definitely, it seems like if you were to pick a point here, it would be steeper to the left and not as steep to the right. So the steeper part's where you're going to get the less distance. So our left side, which is our delta 2 side, is definitely going to be the side that gives us what we want, not the other side, which is going to be kind of more distant to get us the same. Sorry, I know I've drawn this atrociously here. But that's going to give it, we have the same epsilons here. That left side is going to give us the shorter distance between x and whatever, how far apart we are from x. And that's always going to really kind of be the case. If you think about what the graph is doing, the steeper part of the graph is the part you want, because that means you're going to be less far away from whatever x is approaching. So then we do the fun part of writing the proof. So here's our proof. So we are going to say we have proved that the limit x approaches 3 of 4 over x plus 1 is equal to 1 because for any epsilon greater than 0, if delta is equal to the smaller of the two, which was again the delta 2, which is, so I have to be a little bit careful here, right? I can't actually write that. That's not delta 2. That's the negative of delta 2. So I have to say that delta is equal to -4 over 1 plus epsilon plus 4. Yeah. It's always kind of funky. Right, so we were picking delta 2, right? That was our choice. Well, that's negative delta 2, so delta 2 is negative like that. But if that, then it is true that the absolute value of our function minus the limit is less than epsilon, which proves it. So as you might see, these problems are a little tedious, right? There's kind of, it's not like there's a lot to do. Okay, fine. It's not like there's a lot to do, but there is, it's kind of the same work every time, except that it's different every time because you have to work to really isolate that x minus whatever thing. So, yeah, let's do a couple more. Let's not do that. When you say the first way, do you mean like the example before this one? Yeah, I as much as I feel like I should be able to do it this way, I do think it's kind of easier to do it the other way. So let's look at another example. And there was one he did in class that I noted and then kind of forgot about for a second. Let's see where to put those notes. I always am losing my notes over here. Oh, I know where they are. Go. Oh yeah, that one looked interesting. Yeah, I don't know if I like that. So I saw this example from class, which was to prove that the limit as x approaches 1 of 1 over x is equal to 1. Which is a very similar problem to the one we just kind of did. And I feel like he did something strange, which I don't know, I don't feel like I was on board with exactly. So here's the way I would do this problem. So once again, here's what we want to show. We want to show, and again, I'm writing more words I need to here. I want to show that if the absolute value of my function, sorry, the absolute value of x minus its limit, x minus the thing it's approaching is less than delta, then the absolute value of f of x minus the limit, which happens to be the same here, which is one reason I don't love this question. No, it's not long. I find it a little bit, it can be a little bit confusing to be like, oh yeah, the one here is the limit and the one here is what x is approaching, but right, they are different. So that's like your x minus c less than delta, and that's like your f of x minus L less than epsilon. All right, so let's work with both of them. The left-hand part is relatively easy. So it's x minus 1 is between delta 1 and negative delta 2. And isolating x, we get x between 1 plus delta 1 and 1 minus delta 2. So either a little bigger than 1 or a little smaller than 1. Right, we can be on either side of 1 because these aren't one-sided limits, these are two-sided limits. Can we do a one-sided limit? Probably. We can. So let's work over here. We have 1 over x minus 1 between epsilon and negative epsilon. Yeah. So my preference would be to try to isolate x as quickly as possible. But I don't think that's what your instructor did, which is fine. There are different ways to do these problems. So one way to do this would be say, okay, 1 over x is between 1 plus epsilon and 1 minus epsilon. Take the reciprocal of all sides, also changing the direction of the inequality. Say that 1 over 1 minus epsilon is bigger than x is bigger than 1 over 1 plus epsilon. And then, now be careful here. Here's an easy way to make a mistake. I'm not setting these two parts equal to each other because they're not the same side of the inequality for x, right? This is the thing here that x is less than, that I'm pointing to with that finger there. This is the thing that x is bigger than. So if you want to like match up sides of the inequality, you have to write the inequality in the same order. So I can rewrite this as x less than 1 over 1 minus epsilon, bigger than 1 over 1 plus epsilon. And then we can go about the process of solving for delta 1 and delta 2. So let's see here. So setting the positive sides of the inequality equal to each other, we get 1 plus delta 1 equal to 1 over 1 minus epsilon, or in other words, delta 1 equal to 1 over 1 minus epsilon minus 1. Sorry. I suppose if you wanted a common denominator, which I really don't, if you wanted one, you could say delta 1 was equal to 1 minus epsilon all over 1 minus epsilon, which becomes just epsilon over 1 minus epsilon. Not what I'm looking for, but okay. And then similarly, we can figure out delta 2. So let's say that that's equal to that. So then 1 minus delta 2 is equal to 1 over 1 plus epsilon. And then 1 minus 1 over 1 plus epsilon is equal to delta 2. And if you wanted a common denominator, 1 plus epsilon minus 1 all over 1 plus epsilon. Or in other words, epsilon over epsilon plus 1. And then we have, again, we could not find the smaller one. We could just say we're going to pick delta to be the minimum of delta 1 and delta 2. I find it hard to actually do that though, because why wouldn't I just do the work right now? So let's find delta to be the smaller of the two. Again, I don't want to pick an epsilon that's larger than 1 or equal to 1 because then I'm going to have weirdness over here. So let's say if epsilon is equal to 1/2, well, delta 1 would be 1/2 over 1 minus 1/2, which is 1. Delta 2 would be 1/2 over 1/2 plus 1, which is 1/2 over 3/2, which is 1/3. Delta 2 is the winner again. A lot of the functions we pick, delta 2 ends up being the winner because a lot of them are steeper first and then shallower later. That's not really always true. It's a lot of these reciprocal ones are. I think, yeah, I don't even, I don't remember actually seeing what your professor did in class, but he did something different, right? Like I think he got a common denominator here first, and then I don't actually really know. Like it was, yeah, it was a little weird. Yeah. Oh, yeah. So here's what I'll say. I think the way I did it is easier, and more importantly, as valid. So you don't have to find your delta the same way that someone else did. There are many options. My blanket statement would be to do it this way. It's how the textbook does it, and it's usually going to work out pretty well, even if you don't figure out actually which one of these is the minimum. You typically can, usually just by picking any value of epsilon that's valid and then seeing which one's bigger. That generally holds no matter how big or small epsilon is, as long as it's not out of bounds. We still need to write the proof here. We can't just leave this unwritten. So proof, let epsilon be greater than 0 and pick delta equal to epsilon over epsilon plus 1. Then if the absolute value of x minus 1 is less than delta, I always feel like I write the wrong words here. Then the absolute value of f of x minus our limit is less than epsilon. Or in other words, if the absolute value of x minus 1 is less than epsilon over epsilon plus 1, then the absolute value of 1 over x minus 1 is less than epsilon. Which proves the limit as x approaches 1 of 1 over x is equal to 1. It does take practice. Yeah. So I would also recommend, for those of you that have seen this in your class already, to try to write your words in the same style as your instructor, because that is certainly what they'll be looking for if they ask you to write one of these proofs. It is a pretty typical question to show up on a first midterm. Not that it necessarily has to. Some people are like, no, I don't want to ask that because I don't want to grade those questions because they usually don't come out particularly well. But it certainly could show up on your first exam. I've often given it as an extra credit question on a first exam. But you shouldn't be surprised to see this on a first exam if it shows up. Probably a linear example because those are easier to grade. But again, I'm not your teacher, no guarantees. But that's what I would certainly practice this a bit to make sure that you can write out the words and do the work. What else to see in these last? Oh, let's see. Sure. I don't think we have time for another example, but I will point out something else that I'm really buried at. All right, this last. I guess I should ask you all: is there anything that's glaringly that I've not mentioned that you would love to talk about in 4 minutes? Uh-huh. Sure. Okay. So it really depends on what you're being asked to do, right? If you're just being asked to find the delta with a given epsilon, then no, we don't really have to write this proof. But larger context, this idea of this proof is what this section is all about, and actually, right, being able to prove that the limit is what it is, not just find the delta based on the epsilon. I will say though, like for this problem, if we were given that epsilon was equal to 0.1, we could then find the delta that we need. So we could then find, well, we already did the work, right? We found epsilon, or sorry, delta equal to epsilon over epsilon plus 1. So our delta here is going to be 0.1 divided by 0.1 plus 1, which I would simplify, right? That's 0.1 divided by 1.1, multiply the top and bottom by 10 to get 1 over 11. So that means that, great, in this case, if the absolute value of x minus 1 is less than 1/11th, or in other words, if x is between 1 plus 1/11th and 1 minus 1/11th, then we are guaranteed, we for sure get to say, not anyway, red period there, but the absolute value of 1 over x minus 1 is less than our choice of epsilon, which is 0.1. And we can see that, right? Whether you plug in a number as big as 1 plus 1/11th or as small as 1 minus 1 over 11, and we do the subtraction here, we're going to get 1 over 11. And the absolute value of 1 over 11 is certainly less than 1/10.
Delta, and it was kind of done in weird ways, you said it's kind of like absolute value of 1 minus x over actual value of x, and then something with the delta. But it comes out.
Oh, right, because in that one, right, because in that one you're doing this, right? You're doing 1 minus 1 over x, and then writing, oh, sorry, the other way, apologies. Not doing that, you're doing this. You're doing the absolute value of 1 over x minus 1, right? Which then becomes the absolute value of 1 over x minus x over x, which is the absolute value of 1 minus x over x. And yes, you can break that up as the absolute value of 1 minus x over the absolute value of x. Now, we know that the absolute value of 1 minus x is the same as, watch this, the absolute value of x minus 1. Is that okay? If you do 1 minus x or x minus 1, even though one of them is positive, one of them is negative, it's still going to be the same positive or negative value. And then we can say, well, great. We know that we wanted the absolute value of x minus 1 to be less than delta. And then, so we can say, great, that's less than delta over the absolute value of x. But then, what about this? Well, that's where we're going to work with this. So we have x minus 1 between delta and negative delta. Add 1 to everything. And then we do the reciprocal thing again. Oops, I forgot to call this delta 1 and delta 2. And then we can see, well, our 1 over x is less than 1 over 1 minus delta 1. So this is going to be less than delta times 1 over 1 minus, I'm just going to use delta here. That's how we're getting the delta over 1 minus delta. It's a little funky. I really, really, really don't recommend doing it this way. It's harder to kind of figure out exactly what needs to do what. It's much more straightforward just to get the x's isolated in each of the two inequalities and then set the right-hand sides equal to each other, the left-hand sides equal to each other, and then figure out which of those deltas is the smaller of the two things. And I'll say the key to understanding this is to practice it. So if you practice it, you will have a better chance at having a good idea of what's going on. All right, that's all I got for today. I have office hours over in CADS. Come join me. We'll talk about this more.